This lesson will directly build on the last one where I introduced the number e. I will now use this number to describe a quantity that grows continuously. Well, we will only look at financial models, but you can generalize its use to other models of growth and decay, if it is continuous. The skills required to master this lesson are a recall and understanding of compound interest. Let's first quickly remind ourselves of how I introduced the number e. So this was a problem described by Jacob Bernoulli at the end of the 17th century. I'm not going to read it again, it was in the last video. But basically, we took $1 and we invested it at 100% interest rate, that's doubling, 100% interest yearly, but we compounded that n times a year. So the formula is the initial amount, $1, times 1 plus interest rate is 100%, that's 1, divided by n times a year to the power of n. We're looking at the value at the end of the first year. And then we looked at what happened in this formula when n is very, very large. You can try on your calculator. And this formula will lead to the number e, 2.718, etc., etc. When n approaches infinity, instead of saying that the compounding happens each individual moment, as Jacob Bernoulli stipulated in his problem, we will say compounded continuously. So let's now imagine that you take an initial investment of P0, you put it in an account where you have a yearly interest rate of R, usually described in percent, and you also assume that the number of compounding each year is n. The question is, what happens if you want to look at continuous compounding? Instead of having a finite number of compounding, we want to look at continuous compounding. So first, let's write the formula for what we have at the end of t year if we have n compounding a year. So again, I'm looking at the end of t year. How much will I have in my account? Well, P0 times 1 plus R over N to the power of NT, right? This is the compounding n times a year formula. Okay, what we want to do in this formula is make n very large, okay? N has to become larger and larger. So first, before I do that, I'm going to do a little trick that we've done many times before. I'm going to break my exponent right here. So I have P0 times 1 plus R over N to the power of N, and then right here to the power of T, right? Now, if you remember the first video, what did we say? We said that if you looked at 1 plus 1 over n to the power of n, this quantity approaches e. This quantity approaches e. Now, right here inside, we have a quantity. It's not the same as that, but it is not difficult, and you can do that in pre-calculus, it is not difficult to show that this quantity approaches e to the power of r. Okay, a little change of variable will do it. This approaches e to the power of r as n approaches infinity, of course, as n grows very, very, very large. What happened right here, right? Remember, we took n very large to see e appearing. So this formula, if n grows very large, it will go towards P0 times er to the power of t. This is not how we normally write it. We write it as P0 times ERT. That's it. This is a formula that describes how much you have after t years in an account with an interest rate of R, initial investment P0, but now it is compounded continuously. E here indicates continuous growth, an amount that continuously grow every fraction of a fraction of a fraction of a second, or as Jacob Bernoulli said, each individual moment. All right, that's the last formula for compound interest. Let's apply this formula to a couple of problems. Okay, here is the first problem. You invest $10,000, interest rate 6.5% compounded continuously. So this is a yearly interest rate, but it's compounded continuously. How much is your investment worth at the end of 10 years? Okay, let me write the formula we just went over. PT equals P naught times E to the R times T. Okay, what do we know? This is a future value problem. I want to know how much my investment is worth in 10 years. So I'm looking at P10. T equals 10, right? I also know my interest rate. R is 0.065. And finally, I know my initial investment. P naught is $10,000. Okay, now it's just plug and chug. P10 equals $10,000 times E, we know what E is, right? 2.718, right? To the power of RT. So R is 0.065 times how many years? 10 years. Here we go. And that is going to be the investment that you have at the end of 10 years. Let's take the calculator. All right, so I said 10,000 times E. So how do you type E to a power in your calculator? Well, look at the third button from the bottom on the left column right here. This is ln. It says ln. And on top of it in blue, it says e to the x. This is what I want, so I'm going to type second ln. Here we go. Here's my e. The interest rate was 6.5%, so this is 0.065, and it was in 10 years. So this is a future value. You know how to round it. So it is $19,155.40. Let's report that. So first of all, it's not an equality. It is about $19,155.40. Here we go. Answer to the first problem. Let's go over the second example. Now, in this example, you're projected to have $100,000 in 5 years, okay? And you want that because you want to replace some equipment in your business. How much should you invest right now? So this is a present value problem, right? It's a present value question. How much do I need right now? If I'm going to place my money in an account that pays 8.25% interest compounded continuously. Let me write the formula again. PT at the end of t years is the initial investment P naught times e to the RT when you compound continuously. Okay? What do you know in this problem? Well, you know that you want to have $100,000 in 5 years, so you know P5. P5 is $100,000, right? T is 5, right? P5, T is 5. You also know the interest rate. R is 8.25%, so that's 0.0825. And that's it. That's all you need to know. So let's write the formula. You're looking for P naught, right? So we have 100,000 equals the money I'm looking for that I want to invest right now times e to the 0.0825 times 5. I want to have this money in 5 years. So this is now easy to solve. You're going to divide both sides by whatever multiplies P naught. E to the 0.0825 times 5 right here. And you will find how much you need to invest right now. Okay, times 5. Okay, so what is that? Let's do it. $100,000 is what I want to have in 5 years. And I need to divide that by E, so this is second ln. E to the power of the interest rate is 8.25%, so 0.825. And I want to have this money in 5 years. How much do I need to invest right now? This amount. So this is $66,199, and careful, this is a present value problem, so we need to write 32 cents. Okay, so let's report the number. So this is about $66,199.32. Here we go. All right, next question. Okay, by this time you have the hang of it. This time you deposit $12,000 in a certificate of deposit account. You're gonna leave it there for 18 years and the return is 9% compounded continuously. I have to use a formula with E, okay? So you invest $12,000 and you compound continuously, so it's a formula with E. The rate is 9%, that's 0.09, and you leave it there for 18 years. And that will give you how much your investment is worth after 18 years. So let's take the calculator to figure out how much we have. $12,000 times E, that's second ln, to the power of, this is 9%, 0.09, times for 18 years, and this is $60,637.08. So this is a future value problem. Just leave 0.8 after the decimal point. Do not round up or round down. It's just 0.8, okay? All right, let's report that. And so this is $60,637.08. Okay, next problem. In this last example, I want to figure out how much better continuous compounding is versus daily, monthly, annually compounding, okay? How do I do that? I invest $1,000 in an account that pays 5.5% interest per year. And I want to know how much is the account after 8 years. And these are the different schemes I will be looking at. Okay, so A, I just compound annually. So what do we do for A? Well, we take the formula. So P8 equals P0 times 1 plus R to the power of 8, right? So P8 is P0 is $1,000. R is 5.5%, right? So it's 0.055 to the power of 8. Okay, I'll take the calculator and I will write my final values after, okay? B, what do I do for B? In B, I'm compounding monthly, right? So the formula is going to be P8 equals P0 times 1 plus, now I'm compounding monthly, so R divided by 12, right? 12 compounding periods in a year to the power of 12 times 8. And so it's going to be $1,000, that's the initial investment, times 1 plus 0.055 divided by 12 to the power of 12 times 8. Okay, we'll take the calculator to figure it out. All right, now next one is daily. Daily means there are 365 compounding period a year. Okay, so you do P8 equals P0 times 1 plus R. Now this time you need to divide the rate by 365, right? That's going to be very, very small. Yes, but on the other hand, you are raising that to a very, very large power, right? And so in the problem, it is 1,000 times 1 plus 0.055 divided by 365 to the power of 365 times 8. And finally, we compound continuously. So I'm going to compare all of that to P8 is P0 times E to the RT, to this formula right here, which in this problem is 1,000 times E to the R is 0.055 times 8, okay? And I want to figure out how much that is. All right, now we take the calculator and we're going to compute all of that. Now, what I'm going to do right here, because I want to make my life easier here, this is over 1, right? And this is 1 times 8. And actually, I'm going to flip that. I'm going to write 8 times 1. Here, I'm going to write 8 times 12 in my calculator. And here, I'm going to write 8 times 365. I'll just have to insert something there, okay? So let's take the calculator and let's do it. Initial investment, $1,000 times 1 plus rate is 5.5%, so 0.055. And I'm going to say divide by 1. This is going to be my annual rate. Okay, divide by 1 to the power of I'm going to say 8 times 1. Okay, I don't need the times 1 right here, but you'll see, I'll use it later. So this is when I compound once a year, the interest fall at the end of the first year. That's it, that's all. So what is that? This is $1,534.68. So in this case, after 8 years, we have $1,534.68. All right, in the second case, we're looking at compounding monthly, so n equals 12. And you'll see why I did all of that. Put my 8 first here, because now I'm going to grab this formula, I'm going to go to the exponent, and I'm going to add a 2 right here. And then I'm going to bring my cursor right here on top of the 1, actually not on top, but on top of the parenthesis. And I'm going to insert, second insert, and I'm going to put a 2. Here we go. That's monthly. Okay, what is that? $1,551.14. So I said $1,551.14. So you see, it is better, as expected, it is better when we compound monthly than when we compound yearly. Why? Because of interest on interest. Okay, well, let's increase the number of compounding. Now I want to compound daily. So what do we have? So this time again, I'm going to grab my formula right here. I'm going to replace my power by 8 times 365 right here. I'm going to go on top of 12 right here. And I'm going to put 3, 6. And here I need to insert. So second insert and a 5. All right. And that is $1,552.65. So this is about $1,552.65. So again, we find something that is better than the second, but not by much, right? By $1 and something, okay? So it's not much better when we compound every day versus compounding every month. So finally, let's see what happens when we compound all the time, okay, continuously. I need to enter this formula now. And so I have 1,000 times second log, that's e to the power of 0.055 times 8, and it is $1,552.70. So it's barely better than compounding daily. So we found $1,552.70. So it is just 5 cents better than compounding daily. Now, of course, I just started with $1,000 and I just looked after 8 years. If you start with a higher amount, the difference may be a little bit bigger. Okay? Okay, I hope this video was clear. Thank you for watching.